Hi everyone, welcome back to the Flight Engineer YouTube channel, a channel about aviation technology and history. I'm your host John, a mechanical engineer with a minor in aerospace engineering, a private pilot, and an enthusiast for all things that burn gas or go fast. As we dive deeper into the fundamentals of internal combustion engines, I want to focus on the theme of compromise in design. Engineering at its core is about balancing conflicting goals and requirements. The combustion engine itself is the perfect example of this balancing act in practice. In this segment, we'll start with the most basic requirements to be weighed. An engine must convert its fuel into useful work in a reasonably economic way. It must operate whenever it is needed and for however long it is needed. Finally, assuming its purpose is for transportation, it must not be so large or heavy that the unit itself cannot be moved. You may notice that all the engines appearing on screen look very different. That is because they have all made sacrifices or reached compromises to be better in one or two of these areas. The small block V8 will produce a lot of power, the air-cooled VW is light and compact, and the diesel generator will run continuously until the heat death of the universe. One can try to combine all these qualities, and sometimes it even works, but be prepared to part with a significant amount of your net worth to do so. Underneath the web of conflicting requirements, there's one core struggle. An engine has to rapidly release energy from volatile fuel, while at the same time containing and directing that energy such that the whole assembly isn't destroyed thousands of times every minute. Engine designers are constantly riding the razor's edge between peak output and catastrophic failure. This is the battle between performance and durability. To get us started, let's try and understand some basic concepts. Performance can mean many different things, but the most commonly discussed metrics are power, torque, and fuel economy. Power is typically represented in horsepower or kilowatts. Torque is normally advertised in newton meters or pound-feet. And when describing the engine itself, fuel economy can be represented by specific fuel consumption or fuel conversion efficiency. Finally, engine speed in revolutions per second or per minute is not to be overlooked, as it provides operational context for the rest of the performance measures. The definition of power in physics is some amount of work done over a given time, where work itself is a force applied over a distance. So power is a force acting over a distance during a certain amount of time. I find that it's helpful to look at the units to more intuitively understand concepts like this, so I'll provide the breakdown of the dimensions so those inclined can pause and investigate. The practical definition for power in engines is a little bit more complicated, but it simplifies down nicely. Here, we are interested in the amount of work done by the engine over one full cycle, divided by the time it takes for that cycle to be completed. Work per cycle is engine torque times 2 pi radians times a cycle constant. The torque here is just like the work term in the physics equation. They both have units of force times distance, but the torque implies rotational work, or force applied at a distance from a central axis. The 2 pi radians accounts for the torque being applied around one full rotation of a circle. The cycle constant, or the Greek character eta with subscript r, serves to account for the number of revolutions in one engine cycle. This is really only used when cycle work is being calculated by indicated torque. More on that later. It ends up canceling out of the power equation anyway, so we don't need to worry about it right now. So cycle time is just the cycle constant divided by the engine speed n. Finally, putting it together, we see that the cycle constant cancels out of the equation, and we are just left with torque times 2 pi times engine speed. This equation may be familiar to some, but it will make more sense with some units. When torque is given in newton meters and engine speed is in revolutions per second, power will be given in watts or kilowatts when divided by 1000, as shown here. Viewers who are uncomfortable with dimensional analysis may want to avert their eyes, but for those interested, here's how this is derived. For those who prefer to use freedom units, torque given in pound-feet and engine speed given in revolutions per minute can be used to find horsepower with this equation. I apologize for the wall of notation, but if you were ever curious on where we get the 5252 number, here's the answer. Next, we'll discuss torque in more detail. We've seen that torque is a critical factor in the power equation, and while its definition is relatively simple, the way it's measured and represented is not always intuitive. As stated before, torque is a force times a distance, but this has some qualifiers. To fit the definition of torque, a force must act on a moment arm that is a fixed distance away from a center of rotation. This must also be tangent to the path of rotation. This might seem pretty arbitrary, but it exactly fits the visualization of crankshaft torque. This brings us to the engine performance definition of torque, where tau is equal to crankshaft torque, but even this doesn't tell the whole story. We must consider that the force on the crank will vary wildly throughout the engine's cycle. During the power stroke, the force will drive the rotation of the crank, but during all other strokes, that force will actually resist rotation. Due to this, we'll take engine torque to be an average of the crankshaft torque through the whole engine cycle. This notation may look strange, but this is what is actually being measured when torque values are reported, and it can be measured in two different ways: brake torque and indicated torque. Brake torque is the easiest to understand, and it is typically the number being reported when you go to buy a new car or truck. This number is obtained by running an engine connected to a piece of equipment called a dynamometer, or a dyno. A dyno resists the engine's rotation during operation. This can be done with a water-filled fluid coupling, an electromagnetic load very similar to turning a generator, or even just a friction load. Early dynamometers loaded engines with friction elements very much similar to a disc or brake drum in a car. These brake dynos is where the term brake torque and brake horsepower come from. Shown below is a basic diagram of a dynamometer. A rotor within a stator is mounted on bearings. The rotor is connected to the engine and tries to spin the stator. The stator is held back by a lever arm, which itself is connected to the ground. The length of the lever arm is known, and a load cell measures the force applied at the end of the arm. With these two quantities, brake torque can be calculated. With that, crankshaft RPM just needs to be measured with an encoder or tachometer, and then power can be calculated. The second way to measure engine torque is by using indicated values. This is done by directly measuring the pressure in an engine cylinder and calculating the resulting torque on the crankshaft. Today, in-cylinder pressures are measured by high-frequency pressure transducers and complex data acquisition systems. In the early days of ICEs, however, a mechanical plotting device called an indicator was used to analyze the dynamics in an engine cylinder. This leads to the term indicated torque. To find indicated torque, we assume that we're given the cylinder pressure. Pressure is a force exerted over an area, and since this is gas pressure, we will assume that it pushes equally in all directions. We just want the force on the piston, so we will rearrange to find that force is equal to pressure times area, where the area is the piston's crown. So force on the piston due to cylinder pressure is given by this equation. From here, we can assume that the engine is operating at constant speed, or in dynamic equilibrium, and add in all the reaction forces. Ultimately, these will give us the force on the crankshaft itself. Zooming in a little, we evaluate how the two forces present will affect the crankshaft. To do this, we will calculate the moment about the crank's center axis due to the x and y forces. Using some trig, we multiply each force by its distance from the central axis. This gives us instantaneous cylinder pressure for a given crank angle and cylinder pressure. Finally, we can bring back the torque average. This indicated value taken at each degree of crankshaft rotation throughout the cycle and averaged gives us the torque of the engine. Here's one slide to summarize all the equations. Now that we know how performance is measured, we'll look at how we can increase it. Assuming this means making more power, there are three basic ways to do it: increasing engine displacement, increasing cylinder pressure, or increasing the operating speed. As the old saying goes, there's no replacement for displacement. While this may not be completely true, increasing displacement is a very simple and effective way to make more power. An engine can gain more displacement by increasing either the cylinder's bore, the crank stroke, or a combination of both. Changing displacement mainly affects the torque part of the power equation. To understand how, we'll start off by assuming that the engine is operating at constant speed. We'll also assume that our cylinder pressure remains constant as we increase displacement. Since torque is equal to force times distance, either the magnitude of the force or the distance itself must be increased to increase the torque and thus power output. The first way that torque can be increased is by lengthening the crank radius, which consequently increases the stroke length. Lengthening the crank radius moves the point where the piston and conrod forces act farther away from the center. Simply put, the lever arm becomes longer, thus the same force on the piston will generate a greater torque on the crankshaft. The second way torque can be increased is by increasing the bore diameter. This increases the force quantity in the torque equation. Recall that force is just cylinder pressure times the area of the piston. Increasing bore size will increase force overall, as the same cylinder pressure is pushing on a larger piston crown area. Increasing either bore diameter, stroke length, or both simultaneously will increase power output given engine speed and cylinder pressure remain constant. This makes intuitive sense as both factors control the volume of the cylinder. A physically larger cylinder will hold more fuel and air charge, thus more energy can be released in each cycle. While no replacement for displacement was the mantra of the last generation of engine builders, many of the current generation worship at the Church of Boost. Boosting, or increasing an engine's cylinder pressure, or charge density, prior to combustion, is in theory an extremely simple way to increase power. Through forced induction, extra fuel and air are packed into the same displaced volume during each cycle. This extra dense charge then results in higher overall cylinder pressures when combustion takes place. Exactly how this is done and the complications that go with it will have to be discussed later, but the physics here are super simple. We'll assume here that engine speed is constant and that displacement does not change. Naturally, this means that increasing cylinder pressure will primarily increase torque. Greater pressure over a piston with the same surface area leads to greater force on the piston. Again, this increased force is transmitted to the crankshaft, leading to higher torque and more power. Finally, the simplest way to increase engine power is to raise the operational speed of the engine. If we hold torque constant, then every time a full engine cycle is completed, a set amount of work is done. If we can raise the rotational speed, more of these cycles will be completed in the same amount of time, and thus more power will be produced. Looked at another way, a set mass of air and fuel are combusted during every cycle. More cycles in a given duration means more fuel is burned. Intuitively, this must increase the engine's power. To recap, increases in displacement, cylinder pressure, and engine speed all will result in more power output. Many designs leverage some combination of all three methods to reach their intended performance goals. However, engineers looking to achieve higher and higher performance levels quickly run into the issue of engine and component durability. Engine durability is basically the system's ability to operate without failures that would end its service life. This is distinct from something like reliability. An unreliable engine may fail to start when you need it, cut out when pushed too hard, or run rough until it's up to temp. An engine that is not durable will snap a crankshaft in half, drop a valve at high RPM, or attempt to set the new world record at the piston toss. In short, durability refers to the engine's ability to run without catastrophic failure. There are many things that can cause durability failures, so we'll start with a brief overview of the most common factors, and then drill down on the more quantifiable issues. For organization's sake, we'll run down the factors in the reverse order of how they would appear on a bathtub failure curve. If you're not familiar with the bathtub curve of failure, we'll describe it real quick. The graphic is pretty self-explanatory, but all products follow a bathtub or U-shaped curve of failure rate over time. If something is going to fail, it will either do so right away due to design or manufacturing deficiencies, or it will fail far into the future due to wearing out. Underneath this, there's always some flat rate of random failures due to the entropy of the universe or something. On to the general factors of failure. Mechanical wear is one of the more understandable and common causes of durability failures. During normal operation, all the metal components of an engine should be separated by a thin film of oil. However, over time, some metal-to-metal contact will surely occur. As this happens, parts rub against one another and wear. The softer material is worn away. As this occurs to a bearing, cam lobe, or chain sprocket, small metal particles are introduced into the engine oil. Normally, these are captured by the oil filter, but when they are not, they act as an abrasive, increasing contact between parts and accelerating wear. When parts wear away so badly that they go outside of allowable geometric tolerances, failures soon follow. Damage to oil pumps or excessive erosion of bearings can lead to a total loss of oil pressure, followed by a seized or spun bearing. In other cases, wear on timing chains or their drive sprockets could result in the engine's valve train losing phase with the reciprocating assembly. Either failure mode could result in a simple loss of power, or a much more destructive failure like piston-to-valve contact or ventilation of the crankcase. These types of failures, while destructive, typically occur at the end of a long engine life, and so are to be expected. Good preventative maintenance and careful operation can also push this failure mode out almost indefinitely. As long as these failures are not occurring prematurely, they are not of major concern. On a somewhat related note, wear between metal components at high speed causes a great deal of heat. This heat and the thermal expansion that follows it can cause an engine to lock up, sometimes damaging it irreparably. In the most extreme cases, a piston might stick in the cylinder liner and have its wrist pin pulled downward with so much force that it fractures the skirt and the wrist pin bore. While this failure mode is extreme, heat can also be damaging over longer periods of time. An engine will heat up and cool down thousands of times throughout its life. Some individual components, like the piston's crown, can see huge temperature swings thousands of times per minute. Since materials expand and contract when heated and cooled, these components are forced back and forth like a paperclip that is bent over and over again. Like the paperclip, metallic components will begin to crack after severe enough thermal cycling. These small surface cracks may not doom the component by themselves, but they may contribute to a larger failure down the road. To make matters even more complicated, all materials expand and contract at different rates with a change in temperature. Taking this even further, a component made of uniform material can expand in unexpected ways based on part geometry and the nature of the heat source. In short, an engine designer must carefully account for how all materials and part geometries will expand due to the operating temperatures of the engine. For example, one can think of a cast iron cylinder liner in an aluminum engine block, or a forged aluminum piston that is severely heated on its crown, but not near the skirt. Heat must be carefully managed and pulled away from the engine to ensure durability. If not, some variety of heat-related failure can occur at any time during the engine's life. A lesser discussed factor of engine durability is materials compatibility, which concerns the finer points of material science and selection in design. The chemicals present in fuel, oil, and coolant can represent a danger to parts of the engine. This is especially true as operating temperatures begin to rise and reactions take place during combustion. Fuels by their nature contain a great deal of chemical energy and can be very reactive as a result. This can pose a particular danger to elastomer-based gaskets, seals, and hoses. These polymer and rubber components can crack or swell with exposure to certain fuels, leading to irritating leaks or full failures of critical components. Elsewhere in the engine, the high-temp environment of combustion creates numerous unwanted chemical byproducts. These leach into lubricating oil and can become corrosive to the engine's soft metal bearings. In some cases, the compounds in the exhaust itself can chemically attack metal components, like valves along with their seats or guides. This typically occurs only at high-temperature regions around the exhaust port. Finally, there's rust, the chemical process that almost everyone is familiar with. Engines have to operate in harsh environmental conditions, so must be built out of corrosion-resistant materials or coated properly to obtain the same effect. However, sometimes even this isn't enough, as the use of dissimilar but corrosion-resistant metals like stainless steel and aluminum together can create the conditions for galvanic corrosion in a wet environment. Whether it's fuel, combustion products, or just plain salt water that's turning otherwise solid components into Swiss cheese, these processes can all lead to engine failure. Some issues like rust present late in an engine's life, but if there's a critical material selection deficiency in the design, it can present itself very quickly. Alright, now that we've spent far too much time going on tangents and discussing things at a high level, let's get down to the real critical stuff. Mechanical stresses and the loading on engine components are at the root of all durability failures. After all, conditions like heat, corrosion, or abrasion are unlikely to cause a failure if that part isn't under a state of stress. During the design phase, the loads on each component must be accurately estimated and accounted for to avoid immediate failure of an engine. From there, any efforts to increase performance must be pursued without exceeding these design loads, or rapid unscheduled disassembly can occur. To understand the mechanical stresses inside an engine's components, we'll look at the forces involved in an operating engine. These forces can be broken down into two types, equilibrium forces and inertial forces. We'll start by describing the equilibrium forces, as we're kind of already familiar with these. It should be intuitive that the primary forces on an operating engine will be the gas pressure on the crown of the piston and the torque on the flywheel caused by a driven load. As discussed in a previous section, the force of combustion will be the cylinder pressure multiplied by the top surface area of the piston. The greatest amount of force will always be generated in and around the power stroke, but cylinder pressure has an effect on engine dynamics all throughout the engine cycle. When the cylinder is not on its power stroke, positive pressure and sometimes vacuum pressure will actually work to slow the movement of the piston. Forces generated at the piston crown and transmitted throughout the entire crank train are balanced out at the flywheel. We will use a torque load at the flywheel as the stand-in for any driven load that the engine is applied to. When an engine is operating at steady RPM, it should be understood that the force of combustion in one or more cylinders is in balance with the driven torque load at the flywheel. If these forces are out of balance, then the engine RPM will be pushed up or down. This is something that pilots come to understand intuitively in their training, even if they are not consciously thinking about the physics. When you are flying straight and level with the engine set at cruise power, the RPM will remain largely constant. If you pull back on the stick, however, and begin to climb, the engine's RPM will drop noticeably, despite no changes to the engine's throttle position. In cruise, the thrust created by the propeller and engine only serve to push you along on your desired heading, but in a climb, you now need thrust to both move the plane across the sky and fight gravity to gain altitude. The load on the prop in the engine's flywheel has increased, however, since the throttle was not changed, cylinder pressure remains constant. The opposite phenomena can be seen when beginning your descent. As you push on the stick and nose over, engine RPM begins to climb if no changes are made to the throttle. In this case, the aircraft requires less thrust from the propeller and the flywheel because some component of the force of gravity is now helping the plane along. Engine load decreases while cylinder pressure remains constant, and so RPM climbs. This certainly can be complicated by changing airspeeds, wind conditions, and variable pitch propellers, but the core principle remains the same. To simplify even further, think of going up and down hills on a highway while driving your car. Everyone intuitively knows that to maintain a constant speed, you need to give it some gas going uphill and lift off a bit going downhill. In doing this, you are intuitively balancing engine load with cylinder pressure by giving the engine more or less air-fuel mixture to burn. From a physics perspective, we call this dynamic equilibrium. If flywheel torque is high, the engine slows down. If cylinder pressure is high, then the engine speeds up. If both are balanced, the engine doesn't stop, it simply finds a consistent operating speed. It is in motion and balanced, or in dynamic equilibrium. The other set of forces that act on an engine at all times are less intuitive. These are forces applied due to the inertia of the engine's components. A well-known example of this would be the force required to decelerate, stop, and then accelerate the piston up and down through top dead center. These forces can be a bit hard to explain, but bear with me through some notation here, as I promise this will all make sense. All objects that have mass and are in motion have what we call momentum. Momentum is signified with the Greek letter rho and is equal to the object's mass times its velocity. Objects with momentum resist changes in that momentum, and so a force must be exerted to make that happen. In the common notation, a change in momentum is represented by d rho over dt. Don't let the derivative notation scare you. This just means that momentum is changing throughout time. Again, momentum is just mass times velocity, so the change in momentum can be rewritten as we see here. We also know that in most cases, the mass of an object does not change significantly with time. Mass can be considered constant and pulled out of the derivative. So now we see that change in momentum is equal to mass times a change in velocity over time. Change in velocity over time has a much more common description: acceleration. It is now apparent that a change in momentum is equal to an object's mass multiplied by the acceleration it is experiencing. Everyone should also know that mass times acceleration is equal to force. With this in hand, it should be clear that when an engine's component has a change in momentum, there is an inertial force experienced that we can calculate. Okay, no worries if all that went over your head. Just focus on the practical application. Let's look at an engine's piston moving through top dead center. Gray arrows indicate motion here. The engine is turning clockwise, and the piston is moving upwards towards top dead center. The red arrow indicates acceleration. The piston is moving quickly, but speeding to a stop at the top of its stroke, so in this case the acceleration is in a downward direction. The inertial force on the piston is shown by the yellow arrow and is acting opposite to the acceleration. The piston, with its significant momentum, would like to continue moving upwards, but the crank and the rod are serving to slow it down and stop it. Due to this, the inertial force is exerted on the mating components in the direction that the piston was traveling. This serves to stretch the connecting rod in tension. Moving to just after top dead center, the piston is moving downward very slowly at first, but seeing as it is starting from a dead stop, the magnitude of acceleration is extremely high here. The magnitude of the inertial force is proportionately high, as the crank and rod must strain to accelerate the piston from its static state. Finally, in the last pane we see the piston is moving down quickly, but at a relatively constant velocity. Because of this, the magnitude of both the acceleration and the inertial force are low, but they still act in opposite directions. Okay, that was a whole lot of theory to throw at you, so let's look at what this means for an actual engine. To run through some examples, I've put together a super simple engine model. This very roughly approximates one cylinder of the common Honda K20. Component sizes and masses are roughly equivalent to the real-life engine, although geometry has been highly simplified. For this engine model, we're interested in three main things. What is the magnitude of the load on the engine's components? With what frequency do these loads occur? And how do these loads change when the engine's operating parameters change? To answer these questions, we'll start our analysis with equilibrium forces. Let's return to the piston motion equation from the last video. Using this and one new equation to describe the angle from the connecting rod to the vertical axis, we can define the position and orientation of all engine components. Next, we need to understand the forces due to gas pressure. An easy way to approximate this is with an ideal cycle analysis of the interactions inside the cylinder. This is the same simple calculation done in any first-year thermodynamics course, although I've made a couple modifications. If you're interested in the details, I have a whole video about ideal cycle analysis, what it can tell us, and more importantly, what it can't. Check that out to learn more. For now, you just need to know that the cylinder pressures pulled from this ideal cycle analysis have been applied to all 720 degrees of our engine cycle. With our motion and cylinder pressure plots shown next to each other, let's quickly understand what's happening here. In the compression section, you can see that the piston position is rising, and below, the cylinder pressure rises as well. At 0 degrees top dead center, there's no movement in the piston but a significant jump in the cylinder pressure. This is obviously the start of the combustion event. Cylinder pressure remains high for a time, but as the piston begins dropping during the power stroke, so does the pressure driving it. Pressure then drops to just above ambient as exhaust is forced out of the cylinder, and then the cycle ends with vacuum pressure as intake air is sucked into the cylinder. Bringing this all together, we see the two plots overlaid on one another. We know the position and orientation of all components, as well as the cylinder pressure at any point in the cycle. This is actually quite powerful, as we can have a computer perform some simple calculations across all 720 degrees of crank angle. There are many quantities we could calculate from these, but let's focus on axial force in the connecting rod and torque in the crankshaft. The axial load in the connecting rod looks like the inverse of cylinder pressure. This makes sense, as apart from some sidewall forces, the rod always takes the majority of the load from the piston. The values are negative because the load is pushing downward, compressing the rod. We see that just after top dead center, and coincident with max cylinder pressure, the rod experiences greater than 47 kilonewtons of compressive force. This is over 10,000 pounds of load. The crankshaft torque curve looks a little different, as it is affected by both the force on the piston due to combustion and the changing lever arm as the crank rotates. Keep in mind that while cylinder pressure is highest at top dead center, the assembly is also oriented straight up and down at that point, so all of this force goes straight into the main bearings as opposed to working on turning the shaft. It is not until the crank has been allowed to rotate 60 to 90 degrees past top dead center, and the cylinder pressure is still relatively high, that we see peak torque. In this case, we're at about 420 Newton meters, or just over 300 foot-pounds of torque. With our equilibrium loading well understood, we can move on to the inertial loading. While inertial loading can be somewhat challenging to grasp conceptually, it's actually quite simple to calculate. From the last part, we already know the motion of our piston. Taking the first derivative of this, we get the piston's velocity. Taking the second derivative then gives us the piston's acceleration. We can consider this to be the acceleration of the whole reciprocating part of the crank slider mechanism. With the acceleration known, we only need to multiply by the mass of the reciprocating assembly to get our inertial loads. Note that the mass and acceleration of the rotating assemblies should be considered as well, but its effects are primarily on the main bearing loading, so we'll skip that for now. The reciprocating motion of the piston and the upper half of the connecting rod have a far greater impact on engine output. We see from our merged plots of piston position and acceleration that we have peaks of acceleration at top dead center and bottom dead center, but the magnitude is greatest at TDC. The below plots for instantaneous component load only consider the inertial effects from the component's mass. This does not include combustion or cylinder pressure, and you can think of it as the force experienced by a freely spinning engine. Internal connecting rod force closely mirrors the overall acceleration plot above, as there are some side loads, but the vertical axis dominates here. The crankshaft torque plot is fairly dynamic as well, with zero torque input at top dead center and bottom dead center, but significant torque reversals as the piston moves up and down the cylinder. While these plots look significantly more complicated than the equilibrium forces, we have to take their magnitude into account. If we scale these plots to match the outputs from the cylinder pressure forces, we see that the inertial components basically vanish away and are largely negligible. However, it must be kept in mind that these are single data points taken from an engine spinning at 1000 RPM. These values will change radically at different operational conditions, but more on that in a moment. Let's take a moment to recap here. We have two main drivers of component loading, those being cylinder pressure and piston acceleration. Using the methods developed, we can calculate the magnitude of these resulting forces. So far in our analysis, we've seen that the combustion event and its resulting gas pressure are the dominant force, with the inertial forces contributing very little to the overall component stress. Forces from the cylinder understandably peak one time per cycle, coinciding with the start of combustion near top dead center. Inertial forces due to the motion, however, peak multiple times throughout the engine cycle, with larger peaks at top dead center and smaller ones at bottom dead center. For anyone wondering, yes, this is the theoretical principle behind primary and secondary engine balance. At some point, we will have to talk more about this as it applies to multi-cylinder engines and engine balance generally. In any case, the magnitude and frequency of the internal forces in the connecting rod are shown in green. The dashed yellow lines represent torque in the crankshaft and are even more complicated than the rod forces, but we'll leave them aside for now. Let's investigate our third point of interest and play around with the model a little bit. In doing this, we can figure out what happens to these forces when engine operating conditions change. To start, we'll give the engine model three different levels of manifold pressure ranging from 1.5 to 2.5 bar. While doing this, we will assume that engine RPM remains constant and that air temperature does not change due to compression. As we can see, the maximum cylinder pressure, connecting rod load, and crankshaft torque all increase with an increase of manifold air pressure. The key takeaway is that increased torque and loading tends upward in a linear fashion with increased manifold air pressure. It should be noted that this sort of ideal pressure increase is not possible in real-world conditions, as there will be work needed to drive a compressor, thermal losses due to inefficiencies, and a hard limit at which the engine will begin to experience knock at higher temps and pressures. Moving on, we can now hold intake manifold pressure constant while increasing engine RPM. Understandably, increased engine RPM leads to increased inertial loading. The key takeaway here is the degree to which that loading increases. Loads experienced by the engine's components increase by the square of the RPM increase. Doubling engine RPM actually quadruples the rod loading and crank torque experienced, whereas a doubling of cylinder pressure would simply double the resulting forces. If you take nothing else away from this section of the video, just remember that the forces due to combustion increase linearly as cylinder pressure is added, but the inertial forces due to piston motion increase much faster, with the square of increasing RPM. As we will come to see, this fact is of great consequence to the design and operation of any engine. We'll look at a realistic example to put all this together. Assume we take our Honda K20 analog, add a turbocharger, and put it in your car. When you start it up, it idles at 1200 RPM and is operating with roughly atmospheric manifold pressure. The graph on the top is just showing piston motion for reference. The plot in the middle shows force on the connecting rod, while the bottom plot is showing crankshaft torque. The blue lines represent force on the components due to combustion and cylinder pressure only. The red line, on the other hand, includes both cylinder pressure and the inertial loading due to component motion. Running at idle, we see that the blue and red lines sit almost right on top of one another. This is because at 1200 RPM, the inertial loading on the engine is almost negligible compared to the forces from combustion. Now let's take the car out, hop on an on-ramp, and start accelerating. Engine speed rises to 6000 RPM as boost pressure begins to come up. Now we can see that the blue and red lines no longer mirror one another. At this engine speed, the inertial forces are having a very noticeable effect on the overall component loading. The increased manifold pressure is also bumping up our peak rod load and crank torque levels, but it's a much more subtle change. Finally, taking this to its logical conclusion, you drop into third gear and do a full power pull on the freeway. Engine RPM jumps to the rev-limited 8600 RPM, and the turbo spools building a reliable 8 pounds of boost. Again, overall component load has increased, but now we see those inertial force peaks begin to rival the force of combustion itself. This is why engines are limited in their RPM range. Eventually, given a high enough rotation speed, the forces from motion itself can become more destructive than the explosions taking place in the cylinders. This is made even more critical by the fact that the combustion only happens once per cycle, while these inertial loading reversals happen far more frequently. Okay, let's take a break from numbers and graphs for a while and look at all of this from the 30,000 foot view. An engine's durability is largely determined by the forces that it experiences during operation. These forces come from two places. Dynamic equilibrium loads result from the balance of gas pressure above the piston and loaded torque on the flywheel. Inertial loading, on the other hand, comes from a combination of component mass and piston motion. But what influences these factors? Well, gas pressure is largely a function of the cylinder pressure and the combustion event. Component motion is mainly dominated by the speed at which the engine is run. Finally, all of these factors, cylinder pressure, piston motion, and component mass, are baked into the engine's displacement and component geometry. These driving factors should look pretty familiar. They're all key drivers of engine performance. So here's the rub. Improving engine durability necessitates reducing engine load, which means slowing down and minimizing the intensity of actions in the cylinder. Improving engine performance, on the other hand, requires the exact opposite. Herein lies the true challenge of the internal combustion engine. If this balance can be struck properly, all other factors are just an optimization problem. So, are we stuck here? Well, yeah. Right at the top of the video, I said that engineering is, at its core, the practice of balancing conflicting requirements. It's hard. That's why we make the medium bucks. However, engine designers are an especially clever bunch of people, so they've found more than a few ways to address this specific challenge. In the next few videos, we'll discuss many of the unique design considerations and trade-offs used to strike the proper balance here. Moving beyond the structural and dynamic considerations of engine design, we'll weave in fuels, combustion, and thermodynamics. We'll also evaluate how the various factors of engine control, timing, and tuning work to maintain the proper balance. This, and much more, will be explored in the time to come. For now, I hope that this information has been useful. Please leave a comment if there are any questions, or if you would like to see any of these topics elaborated on in their own videos. Like the video if you enjoyed or learned something new, and subscribe to see the next videos in the series. You can also follow me on Instagram, where I post aviation photography, notifications about new videos, and anything else I find interesting. Thank you all so much for watching.